Alright, so in this video we're going to take a look at the double-ended isolated forward converter, and sort of subtitle of that I guess should be the double-ended bridge converter, because that's what we're looking at here. And so there's a sort of bridge converter here that you see, and it's double-ended, and the reason it's double-ended is because it permits power flow in a full wave manner. So you can have power being transferred in the positive and the negative cycles because you have a full wave rectifier on the right hand side. Although that could be replaced with a half wave. I mean, that's doable as well, but I mean, for the purpose of this analysis here, we're going to show that is a full wave rectified sort of topology here. So the main benefit of having a topology like this is that you produce, basically, because you're using the positive and the negative half cycles, you end up producing a waveform on the right hand side, the rectified waveform, that will have double the fundamental frequency when it comes to the ripple. Now what that does is that produces a situation where you can get by with much smaller filtered components. So as opposed to, for example, being at 1000 hertz, if your transistors on the left side are switching at 1000 hertz, your ripple on the right side will be 2000 hertz. And so you can basically use smaller inductors and capacitors to take care of any filtering that you need to do. It also there's also a better utilization of the transformer core, since the voltage VP on the left side can go negative, and therefore it can completely demagnetize the core, which is always a good thing to do whenever you're operating in such with such converters. But the obvious disadvantage of this topology is that it's complicated relative to the single-ended converters. So you see there's 4 switches on the left side, there's 4 diodes on the right side. And so you have to switch these transistors on the left side properly, otherwise you'll run into issues. Then there's the issues of the gate drives as well, because these, well, the S1 and S2 at least, their gates won't be referenced relative to the lower rail, so it's a little more challenging when it comes to driving a sort of floating, I guess you can say, transistor. But still, it's doable, so it's not impossible, but it's just more complicated than the previous case, which is why, I mean, that's a key disadvantage. So one thing to note here is that D, so we always define the duty ratio, D, as being the sort of on time, or the fraction of the period that some transistor is on. But in this case, we define it, instead of in terms of the primary side where the transistors are, we define it in terms of the period of the full wave rectified voltage. So, I mean, at the end of all of this rectification, you're going to get some waveform, let's say, that looks like this, right? And it'll be positive only. So that's why I've kind of drawn it like that. Well, I guess you can't really tell it, right? So it'll be positive only. And so we define the duty cycle in this case as being this thing here, as opposed to being the on time of the switches. And the reason we do that is because it's more meaningful in a situation like this to deal with it this way as opposed to doing it the other way. And you'll see in the waveforms as well that it makes a bit more sense and it's a bit more consistent to do it that way. So speaking of the waveforms, I mean, that's usually what we want to jump into as soon as possible. Otherwise, it's very difficult to understand what's going on. So we'll look at a couple of voltage and current waveforms here. And so what we have is, let's say this is our duty cycle, and we'll keep it sort of simple, which is usually a good idea given fairly complicated topologies. So why don't we take that and then get another one of those down here. And so let's plot up here VD, okay? So VD, and let's plot here VP. So VD, just in case you're not aware, VD is this sort of voltage, I guess you could say the output voltage of the rectifier. And VP is the voltage that is applied to the primary side of the transformer by this diode bridge. Okay, so as we mentioned, VD will be a rectified voltage, right? But VP will be a bipolar, so it'll be positive and negative voltage. And so if we extend this a bit first, and then we consider this voltage, right? So this voltage is going to be rectified, we said, right? So it'll be positive. And again, we're defining the duty cycle in terms of this voltage. So it'll be positive, then it'll be 0, and then it'll be positive, and then it'll be 0, and so on. And this will continue. And so in this case, we're defining this time here as being dt, and then this time here as being 1 minus dt, okay? And so in order to generate something like this, and in order to actually use these in a bipolar fashion, in order to actually do this, to create this voltage on the secondary side, you have to switch Vp a certain way. But before I do that, maybe I should probably label this. We can call this V1 divided by N, okay? Because we're kind of reflecting it across the transformer there. But on this side, on the primary side, the way we're going to switch these is in pairs, right? So we've seen the full bridge converter, and if you haven't already, I'll link that in the description below so you can see how the full bridge converter switches in order to generate a square wave at the output. And so if I switch S1 and S4 in pairs, and then S2 and S3 in pairs, then I can produce, when S1 and S4 are on, and S2 and 3 are off, then I connect Vp directly to V1 through these two switches, and then these two are obviously off. And then on the other hand, if I had turned S1 and 4 on, and turn S2 and 3 off, then I basically connect Vp to the negative. So I basically end up with negative V1, right? So I can produce a bipolar voltage in that sort of fashion, or switching in that sort of fashion. So if I say this is when S1 and 4 are on, and then it goes down. But in this case, what we do is instead of going straight down, we have this sort of intermediate state, which is a zero state. And that zero state, is kind of required. Otherwise, you wouldn't be able to, your output voltage would not look like this square wave. You would just have a straight, because it would be positive and then it would go straight negative. So if I were to take a voltage that looks like this, and if this is 0, then rectifying this part would just flip that up, and it would basically be always on, right? So you need to have a 0 time basically when you're switching like this in order to produce a voltage that is a square wave at the output. And so if we apply a 0 state, and we can discuss in a second how to apply a 0 state to such a circuit, but essentially you would have something that's like this. So this would go up, and then you would have this here for 4, and then you would go over again like this. And so it's a bipolar waveform is the kind of the point here that we're trying to make. Okay, and so this would obviously go up again here, wherever this happens, like this, right? Okay, so again, and this would be V1, because this is on the primary side, and this would be minus V1. And so we said during this time we can say S1, S4 are on, and during this time we say that S2, S3 are on, right? And now during this time where it's 0, you can have one of two states, and it depends really. There's a switching sequence you can go by, and these switching sequences, there's different ways to do them, and different ones have certain benefits. But one simple way to make this 0 is to turn either both of the top switches on or both of the bottom switches on. Right, so you can kind of cycle through the switching states in that sense. So, for example, if I have S14 on, so this is S14, then I can have S34 on, then I can have S23 on, right? So why don't we take a look at that? So if I say S14 is on first, I see a positive voltage here. Then if I say S34 is on, then I see a 0, right? Because this switch will be on, this switch will be on. And then Vp basically is connected to the exact same point across both of these. And so you have a 0 here, right? So then why don't we say this is S3, S4, right? So I went from S14 to S34. Now here I'm S3, S2, right? And then I want another 0 state. And since I'm kind of cycling through, right? So we kept 4 on between these two states. We kept 3 on between these two states. We'll keep 2 on between these two states. So it'll be S2 is going to be on here. And if S2 is on here, then S1 also has to be on here in order to have a 0. Because turning S1 and S2 on will connect this end of the transformer to that end of the transformer, which is 0 voltage. So this should be why don't we call it S1, S2, just to be sort of consistent. S2, and then you would go right back into the S1, S4 for this part here, right? So you have different sort of switching sequences, so to speak. And I mean, again, you can say this is 1, 4, and then this one could be S1, 2. And then there would be a logical sequence to go through in the same sense. So whatever these two states can be changed is the point, because they both produce 0, right? So you can produce this 0 state in this way. So as I mentioned, this topology and this mode of operation basically allow you to make this output inductance small, because the ripple has a double frequency relative to the single-ended converter. So if you kept everything else the same, as far as the switching frequency, as far as all those things are concerned, voltages and such, between this converter and the single-ended converter, this would produce an output inductance, this L here, maybe we can label it L. This output L here would be smaller than it would be in the single-ended converter, because you're operating at a double frequency here. And you can see that very clearly here, right? So this, if I call this dt and I call this 1 minus d, then maybe we extend this. So that means this is dt, right? And so if that's dt, this is t, and this becomes t plus dt, and then this is 2t, right? So you see that the primary side voltage repeats every 2t, whereas the rectified voltage on the secondary side, Vd, repeats every t, right? So we're defining the period in terms of that rectified voltage. And so this this sort of setup allows you to basically ensure that the magnetizing current can change signs, meaning that the flux can be positive and negative instead of just 0 and positive. And that was the 0 and positive case is something that you have in the single-ended converter, because you can only apply a positive voltage to the transformer. In this case, we can apply negative voltage to the transformer, so we can better utilize the core of the transformer. So we can magnetize and demagnetize it in a single cycle, or in a switching cycle, I mean, right? And so, as far as the voltages are concerned, that's as far as we're going to go with the waveforms. But we can look at the current, because the currents are usually of interest as well, right? So why don't we maybe, I guess we can just continue these waveforms a bit further down here, if OneNote will let us, and it will. Nice. So let's extend that there. And we're going to plot I mu, so the magnetizing current. Okay, and the magnetizing current is, it's a sort of characteristic feature of this, I guess you can say. The way the shape it kind of takes on is what I'm referring to, because this shape it's a fairly common thing to see in converters like this, and we'll see it again in the dual active bridge converter as well. And that's kind of what we're trying to do with this converter, is set the stage for the dual active bridge, because that's a very useful converter, and we'll look at that in another video. So what are we doing here as far as this is concerned? So we're applying Vp directly to this inductance, right? This magnetizing inductance. And we know that when we apply a positive voltage, or not, when we apply a constant, let's say voltage, the inductor current increases rampwise, right? So what's going to happen as this positive voltage is applied is that this inductor current is going to increase linearly, okay? And then what's going to happen is that during this time when it's 0, it's going to, well, maybe I shouldn't draw it up like that, because that's going to make it look not symmetric. So let's do it like this. Maybe we do it like this. Sure. Okay, so it's going to be increasing like this, but that's going to be too squished. So let's keep it the way it was before. Okay, so it's going to do something like this, right? Between, well, it's not going to be positive. I'm assuming it's at 0. It shouldn't be at 0. That's the mistake I'm making. Sorry about that. So it's going to go from negative, assuming it's in some steady state. It's going to go from negative to positive, and then it's going to be constant during this time because it's a 0 voltage that's being applied to the inductor. And then it's going to go, it's a negative voltage applied here, so it's going to go negative down to this point here during the same time. This is dt, this is also dt duration. and then it'll go negative constant here, and then it'll increase back up, right? And so the voltage during this time is the voltage that's applied to the inductor. So, or sorry, the slope is the voltage that's applied to the inductor. So the slope during this time is just V1 over L, L mu, that is, right? And so we can call this I mu P and minus I mu P. So those are the sort of positive and negative peaks. And this is I mu, of course. And so it will have this sort of trapezoidal shape, and this is a sort of, and like I mentioned, it's a characteristic feature of this converter as well as the dual active bridge converter. And so V1 over L is the slope here. In this case, it'll be minus V1 over L on this side. So this is minus V1 divided by L on that side, and you can determine this rise and fall time, or sorry, rise and fall magnitude of the current based on this voltage, the inductance, and then this dt here. And so you can find out what minus I mu to I mu P is equal to, right? And so the times are also important to notice here as well. So dt is defined as this thing, and dt is the time it takes to get from minus to positive of the peak current. So at the same time, we can also plot the I2, sorry, IS current, not I2. I was thinking about secondary and I said I2. So what we have in that case is a one-note waveform that kind of is not working very well. So maybe we just make a new one then. And so we're going to look at the secondary current, because the secondary current is important to understand as well, because that's what kind of gives us insight on the output current. Sorry about that little hiccup there, because for some reason OneNote does these weird things where it just glitches every now and again. But that's okay. So I2, what's I2 going to do? So I2 is going to be positive and negative based on the sort of direction of the currents that are applied. And so, sorry, not I2, IS. I keep calling it I2. IS. So IS is the secondary current of the transformer. If we go up here, IS is this current here, right? So IS, when the positive sort of voltage is applied there, this will have a positive current IS. And then when the negative voltage is applied, it'll have a negative current, right? And essentially it'll be very similar to, if not identical to this, except the amplitude will be different, right? So during the time where the positive switch, sort of positive sequence is applied, you have a positive current there, and then you'll have a zero current during this time when there's a zero state there, and then you'll have a negative IS there, and then you'll have a positive, and then you'll have zero, and then you'll have another positive, and it'll look something like this. Right? Right. And so this is, well, we've already labeled that, right? So we don't need to do that again. So this current here and then this current here, of course, are important. So IS is what? IS, I mean, you could just call it IS, but in reality, this is going to be, IS is going to equal I2, right? Because these give no rise to any current. They're just sort of controlling the flow of current and when it flows. So IS equals I2. And, well, the amplitude at least. So this could be I2, and this would be minus I2. And of course we can extend this down a bit. And so we see that we have this sort of shape for the currents, and the voltages here. And of course, based on all this stuff, you can derive a conversion ratio. If you were to take VP and you were to apply the volt-second balance, and again, you'd have to apply it over 2t because this is periodic over 2t, not 1t, right? So if you applied the volt-second balance, you would, and I'm not going to do it here because it's fairly trivial for something like this, you would apply what's the average of this thing, and then what's the average of this thing, and then you would add the two together, and then you would divide them by the period, which is 1 over 2t in this case would be 2t would be the period, so dividing would be 1 over 2t. And then you can go from there and you can develop your expression for your conversion ratio, and kind of use this as use that as a sort of modeling technique for to analyze this converter with. As far as the converter operation itself is concerned, I mean, that's as far as it goes. In a practical setting, this converter is obviously not bidirectional. It is unidirectional. And so for that reason, I mean, it has limitations. So you would apply, I mean, for example, this could be applied in some type of AC to DC type of thing, or even if you just want DC to DC, I mean, it works as well, right? So depending on the modulation and the control of this thing, you can use it as a unidirectional, so you can't transfer power in one direction, but you can in the other. But again, most converters are interchangeable between, well, I shouldn't say most, but a lot of converters are interchangeable between DC-DC or DC-AC type of conversion, just depending on how the switches are controlled. So I hope this was helpful. If you have any questions, leave them in the comments below. Like and subscribe to support the channel, and we'll see you in the next one.